So yes, thank you for the great introduction. I lead up. So before I start, so I work at a company called H2O AI. They're the commercial entity that provides support for the open source package H2O and does most of the development on it. So that ends my commercial portion of this presentation. How many people here have used H2O, downloaded it, and done anything at all with it? Okay, so okay, good. This will be new to lots of folks in. So H2O, just as a, I do have to put up one marketing slide. So H2O is an open source toolkit for doing machine learning and more data preparation work. So it's Apache v2 license. You can download it. You can either go to GitHub and look for H2O AI, and it's version 3 that you're looking for. You can download it and build it yourself, or you can go out to h2o.ai/download, and we have pre-built packages available for you that will install H2O on your local machine, for your Hadoop clusters, for your Spark clusters, for R and Python. So what all does H2O do? Oh, good. The conversion to slides has left some of my boxes blank, but basically, H2O is like a big calculator. You start it. It's an engine. It runs. It turns out it's in pure Java. It has a bunch of REST APIs around it, and you load data into it, do some data preparation work inside of H2O, and then you run machine learning algorithms on top of it and get predictions out. Some things that are kind of special about H2O that you won't necessarily find in all the other packages out there is that everything H2O does by default is parallel and distributed. So when you load up files off of disk, it's loading those in parallel, so it'll actually take advantage of all the CPUs, and it'll eat every piece of I/O bandwidth that your machine has to load that up into memory. It makes very efficient use of in-memory computation. So if you load your data up, we typically get 2 to 5x memory savings. So memory's not cheap, so we put it into memory. And then all the machine learning algorithms are parallel and distributed, so you can run them on multiple machines on multiple CPUs. So we've got some of the world's fastest generalized linear models, some of the first parallel distributed gradient boosting model. All those are available in this free open source package. The other special thing that comes out of H2O is once you learn a model, you can take that model and represent it as a Java object that you can go and take anywhere that you're running a Java VM and use for scoring new samples. So this is often one of the challenges with people that are trying to build smarter products and smarter data products, is how they take their learned model and move it out into a production environment quickly and easily. So this is one of the ways H2O has done that. And we have on the roadmap to support other outputs. Right now it's Java, because Java happens to run everywhere, it seems like, in the world. But we have plans for some other language support and runtimes on top of that. So this is the H2O Software Stack, and again, I've kind of talked about this before, but the whole idea is that H2O goes wherever you have data and wherever you have developers. So you can take H2O, run on your local machine on just a single node, wherever you've got data, it'll read it up. But you can also take it and deploy it into your Hadoop cluster, runs as a long-running map job, and so you can take advantage of that Hadoop cluster and all the CPUs and all the memory added, get access to your HDFS data stores. You can run it inside of Spark. It does the same sorts of things. So we have the exact same library can run in Spark, or you can take H2O as a developer and run it anywhere. So all the Maven dependencies are available for you, and it will actually be embedded in whatever Java application you want. The other place we like to take the H2O is not just everywhere that there's data, but everywhere that there's people, because ultimately people are what are driving this data science and impact that we're all seeing. So this talk says Python. It's because we've revamped our Python API considerably, and I'll show you bits and pieces of that in a bit. But if you are an R user, there's an R API. If you're running it in Spark, there's a Scala and Python APIs. There's also, like I said, these kind of pure Java APIs. It publishes a REST endpoint so you can get at it. So there's all kinds of ways that people, either as data scientists or developers, can get at H2O. So at this point, it's usually where my CEO tells me I've talked enough and it's time to actually do a demo. So we're gonna see if the internet's working today. I have, let's see here. just made a very short demo for here, so we will pull it up and run it. Hopefully this, we'll check our network bandwidth. Oh, good. Okay, excellent. So what I have here is just a simple Jupyter notebook. Is it readable? No, we need to go bigger, don't we? No problem. So just a very simple Jupyter notebook. We're going to read in some data. This is the U.S. Airlines data, commercial airline flights from 1987 through 2013. There's about 150 million records. It sits at about 16 gigabytes on disk. This gives you some sense of the data size. And then over here, if all goes well, this is a little tool that comes with H2O. So I'm running this on an 8-node, so 8 compute node cluster at Amazon, each with 8 CPUs. So we will just run through this notebook real quick. We'll import H2O. Here what I'm doing is I'm taking the Python API, the Python client, I'm connecting to the H2O cluster over REST, and that's all it did. So it told me, hey, look, you've got about 188 gigs available and 64 cores in this cluster. So now we're going to import that file that I have, and if all goes well, we'll see these all light up. This is actually loading out of S3, which is a network data store, but so we're loading here, H2O's loading, they said 150 million records, about 16 gigabytes on disk. It's putting it up into memory and it's compressing it, and it's preparing it for doing future calculations on. And if S3 behaves well today, this takes about 45 seconds for 16 gigabytes of data. So we'll give that a few seconds here. Nothing like watching the water meter run. If you want this to go faster, assuming you don't have network I/O issues, you just add more machines. Like that's the way H2O works. It's up to, we've actually got some people, the last report was 600 nodes. Yeah, we personally have tested up over 100. At that point you realize AWS becomes expensive. So yeah, so just to prove, like I said, 150 million records. We'll do some very basic data science. So this data is already in a matrix format, so it's ready for machine learning. Kind of H2O loaded things up into an H2O frame, which is a data frame representation that's strongly typed. So if you don't have it there, if you have semi-structured, unstructured data, you'll need to, that's a step before you get to H2O today to go use that. So that's sometimes where people are using Spark or other tools. So we'll split this data. So I just did that, right? I actually took that data and I split it into test, train, validation, split, 50%, 25%, 25%. We'll run summary statistics here real quick on the training data. Again, we see kind of all the CPUs lighting up. And we get out very simple summary statistics. What we actually get out is a bunch of stuff about how the data is compressed in memory. So this 16 gigs in disk sits in about 5 gigs in memory. So there's 20 some odd ways that H2O does memory compression. And then we got simple summary statistics, and we got the head of the data frame, so you can take a look at the sample data frame. So that's all interesting and all. And this is the more interesting part. So I mentioned that we redid our Python API and have launched it literally a week ago. So the day before our conference, we cut this release, which is called Tibrani 3, which is named after one of our Stanford scientific advisors. So we've tried to make, one of the things we heard from the Python community was that the Python community has this really great framework called SciKit Learn, and they really like that framework. It turns out they have another really great framework called Pandas, which is the data frame framework. And R already came with the data frame representation, so it was easy to kind of make H2O fit in there. But the first rev of the Python API kind of looked like the R API, and the Python community said, hey, this is cool, but not where we want to be. So we've completely revamped both the data frame representation and how you interoperate with it and the estimator. So this should look familiar to anybody that does SciKit work. So we'll just load up a generalized linear estimator. I'll build a simple classifier. In this case, I'm going to build a classifier. And the way I know it's a classifier is I specify the family's binomial. in terms of GLM, you can get binomial, multinomial, Gaussian loss, Poisson loss, gamma loss, and Tweedy loss all built into the algorithms. I'm going to do a lasso regression, so I'm going to actually look for a sparse model by setting the alpha parameter to 1. So we'll just create that classifier. I just set up the dependent and independent variables. This is one way to decide how to train your models, name the variables you want to use. So we're going to earlier today, I thought it was great. It was, it's important to ask the right questions. So we have a lot of kind of engineered data in here. And the question sometimes we ask is my flight departure delayed? I'm more interested if I'm arrival delayed. So we'll see if these flights are arrival delayed and do some prediction across this. So I'm going to set up arrival delay by year, by month, by day of week, when the computer thought you would depart and arrive, some elapsed time, origin, destination, and the carrier. So one of the things that's important about this is origin, destination, and unique carrier are all categoricals or factors. And so in SciKit, you might one-hot encode all of these. It turns out that the origin and destination is each about, there's about 300 options, and 768 options in each one of them, and the carrier is 100 some odd options, I believe. So you can imagine this gets to be really, really wide data. H2O actually do that one-hot encoding for GLM for you, so you don't have to do that extra step. And they'll also do all the standardization of the numerical ones. And all of these are options you can turn on and off inside of the software. So we'll build a lasso classifier. We'll train it on that data. And again, like we love showing this off. This is actually running. I'm guessing Auto probably used the limited memory DFGS optimizer, but this is, like I said, parallel distributed, 8 nodes. Usually takes about 30 seconds to run lasso regression on. So this doesn't actually, like what happens is it converges, it reaches the stopping point, so it'll go from 3% to usually 6%, then 100% pretty quickly. And if it doesn't, we'll switch on to the next slide. Still running. The other thing that it's doing under the hood is I patched in a training frame and a validation frame. So I'm training on 75 million records that are with H2O, and I'm scoring in each iteration the other 37.5 million records or so. So all that's happening, you don't have to do this kind of separate scoring step to test your validation. If you're doing infold, it'll do all the infold work for you too. So that's all done. We can look at the output of that classifier. We can see again it was binomial. We can get the data about the training data. We can see that the AUC, the area under the receiving operating curve, is about 0.59. So it's kind of a loose model, not a great predictive model. The confusion matrix for the F1 threshold is automatically calculated. There's several. You can get it for any threshold you want. You can specify the threshold in the binomial models. It also did all the exact same scoring on the validation models and did that in one pass. We can see here the AUC is about 0.59, so we have at least, well, it's not a great predictive model. It is at least generalized across data points. So all of these kind of summary statistics are here. You can see the whole model was built and scored in about 31 seconds. If you want to see the various other things you can do, you can plot out things like the scoring history. So this is how fast the log likelihood in each iteration. So you don't went through 3 iterations of the optimizer until it converged. Predictions are all available. So I'm going to run predictions on the other 38 million records using the model that was just built. I love showing off this thing that's eating up all your CPUs. I did learn before I joined the company, there was a test that was done like this on a Hadoop cluster, and they actually tripped the breaker in the office. So when you take all your CPUs to 100%, you can do all kinds of fun things. All the predictions. So one of the things is that if you do the regression pieces, you'll get single values. If you do binomial, you'll get yeses or nos. In terms of arrival delay, this one, I always love looking ahead of this one because it says you're going to be arrival delayed a lot if you use the F1 cut points. But all the class membership probabilities are also included, both from binomial and multinomial. So those are all calculated too for you, so you can use those. We have people using them in, they have all kinds of different thresholds based on their business goals, or they do multinomial, and they use them for recommendation engines where you're submitting the top 3 recommendations. And those recommendation engines can go anywhere. Adobe presented one where they were trying to do more predictive apps, and they used the top 3 to try to guess which you'd like to take next. We can test on the holdout test data set. Again, we're going to do all that in parallel and do it pretty fast. And then finally, this is the last piece of kind of H2O, which is that model that I just built is in this Java object that you can download and take anywhere you want. And so what you'll see as I scroll through this model, eventually there's a method called score 0. So this is the lowest level API to get at this. There's higher level APIs available, but this is the lowest level. You can pass in new data. The higher level APIs will do the conversions from categoricals to numerics for you. But if you want to do it your own way, you can do it your own way. If not, you can use ours that come with it. So that will score a new prediction in about 90 nanoseconds. So this thing sits in the L1, L2 cache lines of your CPU and will run super, super fast for new predictions wherever you want to take them at. So with that, I'm kind of watching the time here. So yeah, I'll go through a bit more about the architecture of kind of what happened, and then I've provided the conference a much longer deck that actually steps through a very long data science use case that we just won't have time to get to today. But that they'll publish that up on their website, and you can have access to that. And I talked about it at H2O World, so you can go watch videos of it from last week. So what happened when I imported that file is that this is what happened. One single node, if you didn't catch it, from the Python API went out, the Python client went out and talked to one single H2O node and said import that data. And so then it went out and read that data off of disk, not using HDFS in this case, but S3, works the same with HDFS. That data was returned, but there's no data moving back and forth between your client API, Python client and your H2O running cluster. The data stays close to where it got loaded at, and then it's all doing basically remote control. And this is a little bit deeper version of the stack, and each one of those layers of the stack is a place in the open source community where you can go in and you can interject your own code out if you find it useful. So with that, I tell you what, I think I will take questions. I have, like I said, a much longer example. Actually, I want to take a couple things. I'll leave the example out because. So a couple other things that are in H2O that I want to talk about real quick, and these are brand new. So not only, so that here, so that that estimator you saw, that's actually a SciKit estimator. It conforms to the API the SciKit requires you to conform to. So if you want to do really complicated things in terms of cross-validation or scoring examples on cross-validation or setting up multiple steps, we've taken the Python API and we've made it work the same, make it work within the SciKit framework. So that's available to you to use if you don't want to go against the native H2O APIs. The other pieces, there's a new piece that I won't get into too much today, but sometimes you have to do data prep work, right? And so one of the questions we often heard from users was, it's great I can do this prep work inside of this cloud environment of H2O, but then I've got to move it to production and replicate it all. So we've introduced a notion called an H2O Assembly that will actually learn all of those data prep pieces and allow you to take not just a scoring POJO, a scoring Java object, but actually another Java object that represents all of the data conversion pieces that took for it to be ready for machine learning. And this runs, these are all running regular expressions, and we find they run in a few milliseconds in the use case that we have. So that's another thing where you can export a learned model or some sort of model and take it into production. And then, yeah, so this is pretty much what I was saying. So I showed the POJO, but you can also get the assembly Java object out. And then finally, if you're using Spark, how many of you are using Spark? Okay, a few. So if you're using Spark, everything I showed you works in Spark. So we have a version of H2O called Sparkling Water that basically is makes it easy to deploy H2O into a Spark environment. It gives you easy ways to get data in and out of data frames in H2O and into RDDs and data frames into H2O frames and back and forth. But that whole kind of Python API that's that I just showed you is the exact same API in your Spark environment with just a few additions. So that allows you to kind of leverage your skills there. some resources that are out there. So we've had a table, I don't know if it's still open, but we have booklets, yellow booklets, they're great resources. There's the release, which you can go download. There's a ton of examples buried throughout the GitHub repository to go take a look at. And then that IoT example is also out on the H2O World website, so you can take a look. Actually, the H2O training website, so learn.h2o.ai, and you can take a look at a bunch of examples there. And with that, I will close and take questions. Thank you.
I noticed that you have a lot of parallelized operations, and you're running on a JVM framework for doing all calculations. Have you guys ever worked with maybe offloading some of those calculations to GPUs, since you already have everything in parallelized form?
Yeah. So the question is that have we looked at offloading any of this work to GPUs? And so the answer is yes. So so Arno Kandel, which is our chief architect, is looking at that. So we've got kind of baby steps to go into H2O and get it to do that. But one of the things we've got to do is we've got to get out of the JVM, right, to do the native code. So one of the things that people may or may not know about H2O2 is that the founder, one of the co-founders and the CTO is Cliff Click. So Cliff was one of the co-developers of the Java Hotspot virtual machine. So we can make Java run pretty fast, not as fast as a GPU can do numerical calculations. But yeah, so but people that have Hadoop clusters, like this is a great example of things that work really well. So they have a bunch of CPUs and they're underutilized. So.
Is it possible to use this utilization of H2O just for this forever? Say I build all the way some of the platform things for this as a KML, and I just want to use H2O for scoring.
Yeah, so the question was, could you just use H2O for scoring, like you export something out into PMML or something like that? And the answer is no. You need to use the H2O algorithms for building the model and scoring. Any other questions? Oh, there we go.
Where do you think H2O will go with the competition from SparkML?
Yeah, so the question was, what's kind of the competitive position with SparkML? And so I have usually 2 or 3 answers to this, right? And so we're partners with Databricks. We'll run inside the Databricks cloud. We think there's a lot of room for open source machine learning at scale. So we're, the 2 of us really aren't competing against each other. Matter of fact, that's why we went and worked inside of Spark, right? Is that they do other workloads that we don't even begin to touch. The disruptive opportunity is really the closed source legacy providers. So yeah, so we don't view them as competition. Matter of fact, we have examples. There's some really good natural language processing tools in SparkML, and so we have examples where you use those for feature creation and then read them into H2O for actually doing like the classification problems and stuff. So we sit there and play along well with them. Yeah. Awesome. Well, I don't see that there's any more questions. I'll hang around for a little while outside if anybody has any, but thank you for your time and attention today. I really appreciate it.